Hi guys, this is the second video of Introduction to Parallel Programming for Noobs series. In the previous video we talked about what's so important and useful to learn parallel programming. So today we're going to see the easiest case to apply parallel programming. So in the code, in the practice, we're going to use MPI library in C language, and also a virtual machine with Debian that has all implemented there. So let's talk about the trivial decomposition. Is the simplest type of decomposition, as its name suggests. This method does not involve parallelizing the code at all. Rather, the sequential code is run on a number of processors in parallel, with each processor having its own set of input parameters. In order to do, the different instances of the sequential code must be independent of each other. This implies that one version of the simulation cannot depend on the results of another simulation which is being run at the same time. Each processor is working independently and there is no communication between processors. So, let's make an example. Suppose we have this array, let's call it A, with values x0, x1, x2, x3, xn minus 1. And we have a machine, a computer with 4 processors. And we want to distribute this data uniformly between these processors. So let's choose the following order. Processor 0, let's number the processors from 0, have the data x0, x4, and n minus 4. Processor 1 have the next data of each processor 1 value. So x1, x5, data xn minus 3, and so on. So let's see how can apply this. Let's look at this L array, which have 5, 1, 7, minus 100, minus 2, 8, minus 10, and 100. And let's try to find the minimum value of this array. According to the previous decomposition, we have the sub-arrays for each processor. Processor 0, 5 minus 2, processor 1, 1, 8, processor 2, 7 minus 10, processor 3, minus 100, and 100. And each processor is going to find the minimum value of this sub-array. So processor 1 have minus 2, processor 0 minus 2, processor 1, 1, processor 2 minus 10, processor 3 minus 100. So until then we've done a trivial parallelism for calculating the minimum value. And finally, if you want to try to find the minimum value of the whole array L, we need to merge all this value, which implies a communication between processors. This is not the only way that we can decompose the array L. According to our first example of the array A, we can do the following decomposition too. P0 can have x1, x2, x3, and x a quarter n minus 1. Processor 1, teens, n quarter 2, and half minus 1, and so on. So we are decomposing the array in consecutive points for each processor, which is a valid way to decompose this. So let's see a great application of trivial parallelism. According to the previous concept, we need a case when all the values of an array are independent of each other, so we can calculate it in any order and then merge it all between processors, right? So let's assume this case. We want to make integrations, and as we know and we can remember, integration is the same of multiple sums, right? Little intervals of these functions might help us to calculate integration. So let's see it in a geometric way. We have our plane and a function f from a to b, just to put some boundaries. And according to the previous definition, we can take any kind of portion of the any kind of portion to this domain of this function. So let's assume we are calculating some rectangles. Are multiple rectangles with very little, very thin rectangles. Its width is really small. So this is how we can calculate an integration. And let's do it for calculate the value of p using parallelism. So let's see. We have the area of a circle, which is pi by r squared, and assume that r is 1. So the area of a circle is equal to the value of pi. Then for simplicity, we want to calculate only a quarter of a plane. That is also that a quarter of a circle, right? So we have this function from 0 to 1, and this is y equals to 1 minus x squared, all squared. Okay, so we are going to do multiple rectangles to calculate this integral. So the integral that we're going to calculate is pi quarters, right? And multiplying by 4 is the value of pi that we want to calculate. So let's see some code of this integration. By the way, I don't know the exact name of this integration, but let's call it rectangle integration. Why? Because we're going to see some nice methods later. So let's see how can we code it. Okay, so let's analyze this code. We can see that we are adding this new line mpi.h that's going to import the main library for mpi functions that we're going to use in this example. So here we have the main method. We are declaring an approximate value of pi manually to compare and to check how much is the error that we get when we run this program. And these variables we're going to see later how and what are we going to use this for. So the main and most important line of MPI program is this one, MPI init. This is going to tell the computer that here in this line is going to start all the parallelized code, and here in the line 56 it's MPI finalize. That is going to tell the machine that we are finalizing the parallel part of the code. So everything that is between these two sentences is going to be executing a parallel way. Next we have MPI com size. This is an implement function of MPI library that help us and tell us what are the number of processors that we are working. So you see that we are using two arguments, MPI conword and nprox. Nprox is an int variable that will return us the value of number of processors that we're using. MPI conword is the we can say that it's like the communication between all processors. We're going to see in more advanced videos how this communication works. In the next line, we're using MPI comrank. This is used for let us know what is the number of processor we are. So, for example, if you remember the array 8 that we used before, we have P0, P1, P2, P3. So the rank is the number 0, 1, 2, 3. And how, if you want to know which processor you are, you must call this function. For example, we are using the variable myproc, so this is going to tell us which rank we are. And the next lines, we are just reading variable end that is going to tell us the number of intervals we want to work, right? The number of rectangles that we want to calculate. If we can read it from the initial command line of the program when we started, or we can read it later. Okay, so for example, here is a nice sample how we use the rank function. Here we are saying that only the processor that have rank 0 is going to print this message, calculating P using end divisions. What happens if we omit this? If we don't put this if sentence, it's going to print the number of times that we have the processor. So processor 0, processor 1, processor 2, processor 3 is going to print this line 4 times in this case. So to avoid and just print one time, we use the rank function. The next line is a broadcast. The broadcast helps us to communicate to whole processors a value that we want. So check the arguments of this function. We have the value of end, that is our variable that we just enter, the number of variables that we are passing through, because it can be an array also, the type of variable that we are passing, and the communication that we're using. And this 0 value is the processor that we are what's the root from this broadcast, right? So I mean, if you don't get the idea, broadcast is the, for example, if processor 0 have end equal to 5 and we want to know processor 1, 2 and 3 that n is equal to 5, so we are going to broadcast end is one element of type MPI int that we want to transmit the value of processor with rank 0. We want to transmit to the whole other processors, that is the conword. Okay, I hope that's clear. Next, MPI barrier is going to wait all processors to get this point. So sometimes this is not synchronous parallel programming. Some threads, some processors are faster or slower than others. So to have an accurate time measure, we have to put this barrier. Well, then we have to take the initial time, and later we have to take the finish time, just to calculate how much it takes to calculate the interval. So we're defining pi values. Pi is some partial sums of pi. this W is going to be the delta x of our integration. That's going to tell us the number of intervals that we're using. So here comes the parallel part of our code. Look, we are iterating using the first sample of the composition that we show in array A at the start of this video. Check that we are starting from my proc, that it means my rank, my number of rank, until the number of intervals that we want, and this for is going to iterate through to every. It's going to jump the number of processors that we have. So check this out. For example, we have 4 processors. It's going to be the processor with rank 0, going to iterate through 0, then through 4, then through 8, then to 12, and so on. Just like the composition that we show in this video, and the same for the rest of processors. So at the end, we are using all the array, the whole array values to calculate this integral, right? So let's continue. Then x value, we have to define which is the x value that we're using. Then the y value according to our function to calculate pi, and this is going to give us the height of the rectangle. The y value is going to be the height of the rectangle, and we must multiply it by the base or the width of this rectangle. That is going to be delta x, which is w in this code. Finally, this is going to be added to our p sum. Here we have to think like when we declare this np init, all these variables makes a copy. So each processor have its own copy of this variable. So in this p there are 4 variables p that are 0, and 4 variables sum p that are 0 for each processor. So when we are making this sum, it's going to be only for the processors. So we're going to have 4 p sums different each other, and we want the complete sum. We're going to use this function or reduce, that is going to put the npa sum into a new variable sum pi. Again, the number of elements, the type of element, the operation that we want to do. We want to sum all the pi values into sum pi value in using the whole processor, the whole world, all our processors that we're using. So finally, these pi values, if you remember, we are calculating just a quarter of circle, and we want the p value, so we must multiply it by 4, and we calculate the error, just the difference between our theoretical value and our calculate value. Finally, again, we put the condition that we only want to print this message one time, and if you are only the processor when rank 0. That is going to print the value of p and our error and the time that it took to calculate with the number of processors. So let's check it out how this code runs. So here we are. This is the virtual machine. This is a Debian server, and here we have installed the MPI library. So we are going to compile this code. How to compile? Well, we must use MPICC. When we used to compile a C code, we use GCC almost all the time. So this time we're going to change with MPICC, which is an extension of this library. So my source code is called ejemplo 1, and we're going to compile. I'm sorry, we're using the math function, the math library, sorry, and we have to add -1. So let's make run this program. We're going to use this command line to execute it, mpi exec -end and the number of processors that we want to. So we're using 2 processors to start, and to see the difference between time, it must be that more processors, less time to takes to run this code, right? So 2 processors, my program, and the number of intervals. In this case, 1 million intervals to calculate the pi value. So let's see. So we're saying that we are seeing that the time it takes is that 0.1 second approximately. With 3 processors, we're going to see how much time does it takes, and almost that 0.08 seconds. Okay, it's less. Let's see with 4 processors, it must be the half of the time with 2 processors. And yeah, it is. Look, 0 with 2 processors, we have that 0.12 seconds, right? And with 4 processors, 0.06 seconds. So it's correct, our algorithm. If we want to reduce the error, we must add more intervals. Let's see. And we are more precise. Even if we don't, we need to change our code a bit. So please let me a minute. We're going to print with more precision. We're going to compile again. And I'm going to run the code again with more processors, and there you see the error is much less, and well, the time has increased because we're using more intervals. And that's it. How you see trivial parallelism. It's very useful and simple to use. It's a very powerful tool for some numerical applications if you want to. In the description of the video, I'm putting the link for this source code, and you can analyze it at your own pace. And hope you like it. Please share, subscribe, and till the next video, we're going to see more interesting stuff.